Good afternoon, everyone. I'm Xue Junhu. This work is actually by my colleague Chunlei and Yupeng. Unfortunately, he couldn't join us today due to visa issues. I will be presenting our recent work, MGPBD, a multi-grid accelerated global XPBD solver. Deformable simulation is critical for animation, but some scenarios are particularly challenging. Take muscle simulation, for example. Two key challenges stand out: high resolution, over 1 million tetrahedrons, high stiffness. Tightened muscles act almost as hard as car tires. Traditional approaches include PBD, position-based dynamics, and extended PBD or XPBD. XPBD is widely adopted in physical engines like physics, Houdini Vellum, and Bullet. It has three advantages. First, universality. It works for subbodies, clothes, fluids, etc. Just define a constraint and XPBD handles it. Second, simplicity. There are only three core steps: move particles under inertia, solve constraints, update velocities. Third, efficiency. Fast and stable if you just run a few iterations. But for high-quality simulations, issues arise. Sometimes results look too soft, even with high stiffness settings. In the extreme cases, it causes instability or crashes. In subbody simulation, higher resolution and higher stiffness make convergence difficult. XPBD struggles here. It has convergence issues for these difficult scenarios. If we run XPBD under 1000 iterations, it performs well. But if we run more iterations, the residual curve plateaus. It never converges, even with 10,000 iterations. Why does XPBD stall? To understand why, let's examine XPBD's linear system. From Lagrange mechanics, we derive a KKT system from Newton's equation of motion. Taking the short complement of this KKT system gives us the system to solve A delta lambda equals B. XPBD uses a simple approach to solve it, nonlinear Gauss-Seidel or Jacobi, which effectively uses the diagonal of A divided by B. Compared to standard Gauss-Seidel or Jacobi, it makes two simplifications. First, it ignores off-diagonal terms, making it a purely local solver. Second, it uses a single sweep to solve the linear system. This makes each XPBD step extremely cheap, but causes convergence failures in challenging scenarios. Newton's method can solve it well, but it operates in the primal space. Primal space methods solve delta x, the displacements, while dual space methods solve delta lambda, Lagrange multipliers. According to Miles Maclean's research in 2020, dual space systems are more robust to high stiffness ratios, which is critical for muscle simulations. So dual space is better suited here. Unlike XPBD's local single sweep approach, we use a global system solved with algebraic multigrid AMG. Goldenso's SAP is similar to ours, but uses a direct solver, which is prohibitive for large simulations. Multigrid is renowned for fast convergence and scalability with large systems. It transfers residuals between cores and fine meshes, solving low-frequency errors that Gauss-Seidel or Jacobi struggle with. Multigrid has two main types: geometric multigrid (GMG) and algebraic multigrid (AMG). GMG needs geometric relations to define a prolongator P, which is tricky in dual space. In contrast, AMG only needs the matrix as input, so we choose AMG. We tested off-the-shelf AMG solvers like AMGX and AMGCL, but they either failed to converge or were prohibitively slow. We found a key issue behind it. AMG rebuilds P every time matrix A changes, which can take 2/3 of the total time. Fortunately, we noticed A is topology dependent, so it can be reused across subsets. We call it lazy setup. Our experiments showed rebuilding P every 20 steps causes negligible convergence loss. With this and other improvements, our specialized AMG solver is 20 times faster than AMGX. Another key improvement of our work lies in the prolongator, the core of multigrid. As its name shows, a prolongator prolongates. It interpolates low-dimensional core space vectors to the higher-dimensional fine space. From another angle, P's columns span the core space, acting as the basis vectors. A good core space captures low-frequency errors, but how to construct it? We found the near kernel works well. AMG heuristic rules suggest that after sufficient smoothing, low-frequency errors lie in the near kernel, which can be easily obtained with a few Gauss-Seidel sweeps. With this near kernel improvement, convergence speed doubles. Our curve is in blue and the traditional AMG is in yellow. Our algorithm is nearly identical to XPBD, except for the part in the red box, making it easy to integrate into existing XPBD solver. Here are the results. Bunnies of varying resolutions recovering from a flattened state. XPBD explodes at the highest resolution. This shows a relative residual history for the bunny experiment versus iterations on the left and time on the right. XPBD curves stall while ours drop to the 10 to the power of -6. We show that our method handles larger dt without softening in a beam bending experiment. On the right, we show that our method is able to handle collisions as XPBD due to the same input and output. In summary, compared to primal space method and XPBD, ours is more stable and maintains stiffness and high resolution at high stiffness. This is the final result of our human muscle simulation with 1.66 million tetrahedrons and 10 to the power of 9 stiffness. We set 20 iterations and it takes about 40 seconds per frame. Key takeaways: MGPBD combines dual space, global solver, and AMG. It solves XPBD's failure cases under high resolution and high stiffness. We use lazy setup and the near kernel to boost AMG. One major limitation is that each step of our global solver is too heavy, losing the lightweightness and flexibility of XPBD. In addition, AMG is purely numerical, less physically intuitive than JMG. In the future, we want to design a dual-space matrix-free JMG solver. The core remains the prolongator. Finding a good subspace is the key. Our code and paper are open-sourced. Chunlei and Yupeng will join us remotely for Q&A. Feel free to ask them for more details. That's all. Thank you.